This is Psych 522. It is October 22. And today we're going to talk about unsupervised learning, specifically principal components analysis. Quick recap of what we talked about last time. Last time we talked about lasso regression, and we also talked about ridge regression. Okay, and those were penalized regression methods. So you recall that we issued a penalty on the regression when minimizing the sum of squares. And that took the form of specifying a lambda or equivalently an S value. And that introduced a little bit of bias into our estimation, but it helped reduce the variance a little bit. So we said that the ridge regression and lasso could actually be used for cases where you might have collinearity and you'd like to do something to facilitate model selection. And we said that the lasso will drive coefficients all the way to zero. So some of the coefficients will be driven all the way to zero. So sometimes we say that lasso regression is better for predictor selection than is ridge. But also we said last time that, I mean, if some of your coefficients are going near zero, well, that may be sufficient for you to just drop them from the model. Okay. So again, the focus of last week was on that model selection, predictor selection, which is a pretty big area. So getting into unsupervised learning, just want to quickly do that recap again of what we were talking about with eigenvalues and eigenvectors. Okay, so because we're going to come across that in this chapter, we're going to come across eigenvectors, we're going to come across eigenvalues. So here's our eigen value right here. And there it is, right there, eigenvalue. So there's eigenvalue, okay? And this is going to be our eigenvector, okay? This is going to be our correlation or covariance matrix that we're putting into the equation. Now, this is a very, very general equality, okay? So eigenvalue and eigenvector decomposition of a matrix is a very, very common thing, and it's seen across many statistical methodologies. So it's not unique to principal components analysis. This actually is the underground of a lot of statistical methods where you wouldn't even think you would see it. So in discriminant analysis, this is going on. Even to some extent, analysis of variance, you can consider it to be an eigen decomposition. So this underlays a lot of things, okay? So it's a really, really important equation. For our purposes in this chapter, when we do an eigen decomposition, we're doing it for the purpose of getting the actual principal components. Okay, so there's the first distinction to make is that this is common across many statistical methodologies, but for our purposes in doing the PCA, we're specifically interested in the eigen decomposition because it's going to give us those raw components that we want. Okay. And we said last time that you can have x1, x2, x3, x4, okay, a whole bunch of variables up to xn. And the idea of PCA, okay, the idea of principal components analysis is to reduce the dimensionality of this set of variables. So you can put it into a matrix form, and there's x1 up here, x1, x2, and here you'll have either variances, okay, either variances, or you'll have correlations right here. So this is a correlation or covariance matrix. It is in n different dimensions, right? We have n different dimensions to this. So there's one dimension, there's another one, up to however many variables you have. These are observed variables, right? These are measured variables. So maybe you have people's math score, people's verbal score, some other scores. You have a whole bunch of variables. And what you'd like to do in PCA is to reduce the dimensionality of these variables. So what does that mean, reduce the dimensionality? Well, what it means is you'd like to express the information in this matrix in fewer than n dimensions. Okay, you'd like to express the information in this matrix in fewer than n dimensions. Now, why would you want to do that? Well, if you have, say, only 3 variables, you probably don't want to do a principal components analysis. You might want to try it, but you don't necessarily need to do that because you only have 3 dimensions. But as the dimensions increase in number, you're trying to see if you can represent the variables in fewer than n dimensions, and partly for parsimony, right? Partly for parsimony. So imagine if I told you instead of having 1,000 dimensions, I can express most of the information in the matrix with only 2 dimensions. So imagine I took those 1,000 variables, I issue a transformation on those 1,000 into 2 dimensions. Well, that's a little bit more parsimonious than having to look at those 1,000. So you think of that as dimension reduction. Dimension reduction. Okay. So even in the case of what science is about, it seems like an attractive thing that you may want to do. Now here's the thing, and it's not a small issue, that when you actually reduce the dimensionality, okay, you're usually going to lose information. Okay, so there's a cost to reducing the dimensionality. When we subject the data to a PCA, what we're going to find is that if we subject 1,000 variables to the PCA, we are going to get how many components come out of this? We are going to get 1,000 components. Okay, that's the most important thing to understand as we start this off. All PCA does is re-express the information into different components than the original n components, if you want to think about it that way, right? So you have 1,000 variables. When you do the PCA, you're going to have 1,000 components. It's going to extract 1,000 components. Now, why did I put a 2 here? I put a 2 because what you're hoping as is the 2 or 3 or 4 components, however many, expressed most of the info. Most of the info, that says most of the info in the original 1,000 variables, right? You're hoping expresses most of the info in the original 1,000 variables. Now we need to define what we mean by most of the info. Well, what's the information, first of all? Well, what PCA does is it looks at the variances of the variables. So X1 has a variance, X2 has a variance. Okay, I'm just going to look at those 2 variables right now. When we do a PCA, we transform this data into component 1 and component 2, and we're trying to re-express the variance into these components, but in such a way that what you're hoping, at least, is most of the variance is featured in component 1, the principal component, right? That's how you can think of, why is it called principal component analysis? Well, it's the principal component that you're trying to get. You can think of it that way because it's like, if most of the variance is in C1, then maybe you don't need C2. You can drop C2. Okay, so you start off with 2 variables, you do the PCA, which is a transformation. You're doing a transformation, and you're hoping that most of the variance in the variables loads on the first component. Now you're thinking, you may have seen this before, factor analysis and stuff like that. It's not the same as factor analysis, and we'll talk about that near the end of today's class and into next week, but it's not the same as factor analysis. This is a re-expression of the variance, and we're going to see factor analysis does something a little bit different. So let's say that this first component expresses 80% of the original variance, and this one is 20%. Well, the sum of these 2 variances is equal to the sum of these variances here. So variance 1 plus variance 2 is going to equal to these variances of the components C1 plus variance of C2. It has to be that way in principal components analysis. So recognize that we're actually not selecting the number of components. at first, we're simply transforming the information. The selection of how many components you actually keep from the analysis is entirely up to you. And it can actually be difficult, and oftentimes it's subjective on how many components you may choose to keep. But the computer or any algorithm isn't going to do that for you. You have to make that decision. So if you select the first component, well, you're keeping 80%, but you're losing that 20%. So that's why I said just a second ago, I said there's a cost to data reduction, right? There's a cost to data reduction. When you reduce the data down to fewer dimensions, you're going to lose some information. That's like a really, really fundamental principle of doing any kind of data reduction. You're going to lose information unless you keep all the dimensions, but then you're not reducing the data, right? If you keep all the dimensions, all you're doing is transforming the data into new variables, right? New components, but you're not reducing the data. So rarely would a researcher want to take X1 and X2, transform them into C1 and C2, and keep both components. That wouldn't really make a lot of sense. Because then if they wanted to just keep C1 and C2, why don't they just keep X1 and X2? Why do the transformation at all? Right? The purpose of the transformation is so that you can reduce the data. Now, this idea of data reduction, right? Data reduction, you know, it may seem new, it may seem, wow, that's what this PCA is all about, principal components analysis. But when you think about it, and to give you some context for this, data reduction happens all the time in statistics. Okay? It happens all the time. So it's not a principle that's universal to principal components analysis. And, you know, if we give an example, you know, 5 plus 6.2 plus 7.8 plus 10.2, well, if I look at these data points here, and I compute an average on these data points, so I compute the mean, what am I doing? I'm doing data reduction, right? I'm doing data reduction. I'm taking these 4 points, putting them into the mean, and I'm expressing this as one single number. That's reducing the data from these 4 points to this summary idea. So the idea of data reduction is definitely not new, and we do it in graphs as well, right? When we choose interval sizes in graphs, we're definitely doing data reduction. It's a reduction in the number of observations to some kind of summary form. And of course, we do it with the variance as well. The variance is reducing the data. So in principle, what we're looking at is not that different than ideas of data reduction. It's just that principal components analysis goes about data reduction in terms of expressing the variability in the variable. So it's a very specific way of reducing the data in that way. Okay, so what does unsupervised learning mean? Well, unsupervised learning, okay, unsupervised learning means that you're kind of letting the algorithm do the work of trying to find patterns in your data. Okay, that's a fair definition of what unsupervised learning means. So, you know, if I have a whole bunch of data points right here, there's like a whole bunch of data points that I have. Well, when I do like a discriminant analysis, for instance, when I do a discriminant analysis, I take my data, well, I have a grouping variable. So there's my function, 0, 1 is my binary variable, and then I have, say, x1, x2, and x3. I'm using these set of predictors to predict group membership. This type of data analysis is usually called supervised learning. Why is it supervised? It's supervised because I'm offering the algorithm, the mathematical procedure, some guidance on what to do, right? I'm saying, take these variables, see if you can classify them into 0, 1, see if you can predict into 0, 1. Linear regression is another example of what would be called the supervised learning idea. The unsupervised learning is when I don't have anything like this. Here, there's no dependent variable. There's no independent variable. It's just a blob of data. And what an unsupervised learning algorithm does is you set it into motion and you try to find patterns in the data. Okay, you try to find patterns, you try to find groups, you try to reduce dimensionality in some way, but it's not like this. So in other words, in the unsupervised, you typically don't really have a hypothesis. Okay, that's a good way of thinking about it. There's really no hypothesis in here. So you're going to set the algorithm in motion. Now, I just want to issue a caveat on that. I say you don't have a hypothesis. You may have a hypothesis, right? You may think that there's going to be 3 components that come out of this. That's a hypothesis. When we look at cluster analysis pretty soon, you may hypothesize that there's 4 or 5 clusters in this data. So in that sense, all of a sudden, this looks a lot like supervised learning because you have a hypothesis. So the idea of supervised versus unsupervised, I mean, just like so many things, right? It becomes fuzzy. It becomes fuzzy. It's a kind of a useful distinction, but so long as you don't take it too seriously in what you're doing, right? This general difference here is usually enough to kind of appreciate the differences. But as I mentioned last week, I think if you start talking about these a lot and push the boundaries of what they actually mean, you're usually going to find that which one actually wins over. Which one, if you had to classify most analyses into unsupervised or supervised, you're probably going to find that most analyses in the end, to some extent, are supervised. Okay, because we usually have some kind of an idea of what we're doing, and we also have to specify the algorithm in such a way that we're issuing it commands. So you're specifying, when you specify cluster analysis, as we'll see, you usually have to specify, go see if you can find 4 or 5 clusters. That's very supervised like. When we do exploratory factor analysis, mostly next week, well, you're still going to usually give the computer some idea of how many factors you want to find. You're going to have to enter some kind of information, and that has a very supervised feel as well. Okay, so but those are 2 general distinctions, or a distinction between 2 terms that you should be familiar with. So let's get on with principal components analysis, and again, we're going to be getting to clustering pretty soon. So the challenge of unsupervised learning, we just talked about that. The challenge of unsupervised learning is just recognizing that the word isn't always descriptive of exactly what you're doing. We've talked about this. Okay, so that's the part, right? That part is what I just talked about. Going, I'm not quite sure about, all of this, whether this is completely, I mean, we could break this down easily if we really got critical about it. When they say, when we fit a predictive model using a supervised learning technique, is then possible to check our work by seeing how our model predicts the response on observations not used in fitting the model. However, in unsupervised learning, there's no way to check our work because we don't know the true answer. The problem is unsupervised. Again, we could break that down and talk about it a lot and kind of invalidate that statement right there. Because if you do an unsupervised learning technique, like principal components or cluster analysis, you can double check that on new data. You can even validate the solution. So when they say there's no way to check our work because we don't know what the true answer is, well, there is if you have a theory as to what the true answer is, right? If you think there's 2 clusters of patients, COVID, people who have COVID and people who don't, you can run the cluster analysis and then you can validate that solution on new data. So again, fuzziness there in what they say, but useful to just know the distinction in general. Principal components, so here we go. We're going to talk about PCA. That refers to the process by which principal components are computed, which we've briefly talked about, and then subsequently used in understanding the data. So data reduction technique, it's useful as a tool for data visualization as well, as we'll see when we look at plots. What are principal components analysis? Well, we've covered this in some detail. Eigenanalysis. This is one way of getting the principal components. It's not the only way of getting them, but it's a very common way of getting the principal components. There's another technique, SVD, singular value decomposition, that could be used, but they're both getting at the heart of it, of getting these components. So we've got a lot of scatter plots, right? We've got this many scatter plots and produces a lot of plots. So if P is large, then it's certainly not possible to look at all of them. So we want to break down and do the dimension reduction. Here's the key, which we've talked about. We'd like to find the low dimensional representation of the data that captures as much of the information as possible. And when you see information, you should be like, what? What's information? Right? What do you mean by information? Well, information in the language of PC is going to be variances. Okay, it's going to be variances. This is information as far as PCA is concerned. So what you could replace this is captures as much of the original variance in the data as possible, and that would be a fair substitution there. So it finds a low dimensional representation of the data that contains as much as possible of the variation, right? There they go. They say variation right there, information. PCA seeks a small number of dimensions that are as interesting as possible, where the concept of interesting is measured by the amount that the observations vary along each dimension. So what's interesting? Well, that may be up to you to decide as a researcher, okay? Now, you can think of PCA as being entirely atheoretical, or you can think of it as kind of supplementing your theory. So, you know, the computer, the algorithm will do it. It has no problem doing it. It's what you make of it that matters, and that's half the battle, right? You can run the PCA in like 0.2 milliseconds. It's what the result actually means on a research level that's really going to be the most challenging part. So when they talk about as interesting as possible, well, you're going to have to decide whether those components are interesting. Especially in psychology, doing PCA and its kind of overachieving cousin factor analysis, it's especially difficult sometimes to make sense of components. That's in psych. Now, in other areas where PCA is used, sometimes it's very easy to make sense of it because the PCA is actually operating on a physical object. So I'll give you an example. If you have like a digital image, so here's an image of somebody right there, and the image has a whole bunch of like pixels and stuff like that in the image. I can't draw pixels for some reason here. These are a whole bunch of pixels. Well, it's possible to extract principal components from the image. So if I extracted components from the image, then it helps to know how the image is being kind of deconstructed, what those components might represent. So if I took out component 1 and all of a sudden this turned from color to black and white, well, maybe it gives me an idea of what component 1 is. I go, geez, that has something to do with color, because I can observe the actual image change, right? That's harder to do with psychological variables or economic variables or sociological variables, because you cannot usually observe the change in the object, right? You can't observe the change in the object directly. You have to look at the component, and you have to look at what are going to be called the weights of the component to try to make conclusion of what's coming out of it. So it becomes really, really challenging in psychology and other sciences to sometimes make sense of what these components are. So what's interesting is often going to be a subjective thing and decision made by the researcher. But again, principal components analysis will do the procedure. It doesn't mean the components will necessarily be interesting though, right? So if I take nonsense data or just any data set, there's my whole data set, I can do a components analysis on this. It does not mean it will necessarily be interesting. Could just be a waste of time. Whether it's interesting is for you to decide. So the first principal components of a set of features, what's a set of features? A set of variables. Okay, in the machine learning literature, which this book surveys a little bit, and they talk about machine learning, they like to call variables by the name of features. It's kind of an annoying convention, because why call it something new? These are variables. They've always been variables. So you can just think of them as variables, and I usually refer to them as variables. I really just don't like the word features. Is the normalized linear combination of the features, okay? So of the variables. So there's variable 1, there's variable 2, and there's variable P. What's a linear combination? Well, here we have a weight. Here we have a weight. Here we have a weight. Now you look at this, and when you take the weight multiplied by the variable plus the weight multiplied by the variable, these are all different weights, right? These are all different weights. You get Z1. So it's a linear combination of these particular variables or features. Now you look at that and say, that looks familiar. We've studied linear combinations before. We studied them abstractly when we talked in Fox, in the appendix, but we also talked about linear combinations when we talked about discriminant analysis, when we talked about MANOVA, right? In MANOVA, what was the idea? In MANOVA, we wanted X, 0, 1, 2 as a grouping variable, and Y1, Y2, Y3 as dependent variables, and we wanted a linear combination of those dependent variables. So this idea of a linear combination is definitely not new. We've seen it before in MANOVA and discriminant analysis. So what we're doing is creating another linear combination. However, the linear combination that we're producing here is different than the linear combination that's produced here. So it'd be a huge mistake to just think that whenever you hear the word linear combination, you're talking about the same linear combination. Okay, that would be a mistake because different linear combinations are constructed so that they optimize different functions. This particular linear combination that we're going to construct is being constructed in a very particular way. So these weights are being chosen in a very particular way. The weights that we chose for our MANOVA or discrim are chosen in a very particular way. Okay, you might remember that the weights chosen in discrim were chosen to maximize separation on the groups. That was the purpose in choosing the weights, right? That's the function that was optimized. Is the goal of MANOVA or discrim was to select scalars so that you're maximizing group differentiation, right? We're doing something very similar here, but these weights are being chosen differently. So linear combinations are all over the place, right? They're all over the place. They're not just specific to principal components analysis. They're not specific to discrim, to MANOVA. They're all over. So the question for us is to look at this and say, well, how are we going to choose these weights, right? What criteria is going to be satisfied in the selection of these weights? What do we want to optimize? Remember, we've talked before that in many statistical procedures, they come down to optimization problems. What do you want to optimize, right? So, if somebody on the street says to you, hey, I'd like to construct a linear combination of variables. Your question to them is, well, what would you like to optimize with that linear combination? What function would you like to optimize with the linear combination? And then that person is going to say, what do you mean by optimize? Well, what do you want to minimize or maximize? And so you see that it's not enough to just compute a linear combination. You need to compute a linear combination with some imposed constraint of some function you want to optimize. Otherwise, these weights can be whatever they want to be, right? You can choose these weights to be anything, but you definitely don't want to do that. You want to do them with a purpose. Remember, we've talked briefly before about when you do like an IQ test or when you score an IQ test. I haven't looked at the WAIS IQ test in years, but let's say that you're summing up the different scales. Okay, let's say you have, say, 3 scales. You have scale 1, you have scale 2, and you have scale 3. Okay, so let's say you get one score here, another score here, another score here. Well, let's say you get the sum of those to get the total IQ. So you sum these scales. What are you producing? You're producing a linear combination. Only that when you're producing the linear combination, you're assuming the weights are equal to 1. This case, we're going to have weights different than 1. We're intelligently selecting those scalars. Okay, but again, the idea of the linear combination is definitely not new. One thing we want to impose here is we want to impose this normalization constraint. Now, the normalization constraint means the sum of those squared loadings is equal to 1. So that's what that's saying. The sum, of those squared loadings is equal to 1. Now, why do we want the sum of squared loadings to equal to 1? The reason why we want to impose this particular condition is that if we did not impose any condition here, these loadings could be made as large as we want them to be. So they can be kind of like artificially inflated. So what we're doing with the PCA is we're telling the PCA, select those weights, but subject to this condition. And in a sense, that's to get a handle on the weights. Right? Otherwise, they can be inflated without bound, and everything kind of just, it's kind of like, wow, free choice on the weights. No, it's not free choice on the weights. They have to agree with this constraint. The sum of those squared loadings, using the word loadings now, sum of those squared weights has to equal 1. Okay? And that's the imposed constraint that we're putting onto the principal components analysis. So that's what they talk about here. We constrain the loading so that the sum of squares is equal to 1. Otherwise, since otherwise setting these elements could result in arbitrary large variance. So that's exactly what we just said. We want to constrain them. So there's our data set. It's in that matrix right here. We have a whole bunch of variables in there. We assume that each of the variables has been centered to have mean 0. That's the column means of X are 0. Now, the centering is usually done by software automatically. You can actually do PCA without centering. It's nice to have centering features in the data, as we're going to see. But this is something that, depending on the program you're using, is usually going to be done by default for you. So you don't have to worry about that. So there's our linear combination again. We're going to have a linear combination that we are extracting. And what you're hoping is that linear combination, when you get this particular sum, right? This is a sum. This becomes the component, right? The component is that sum of those weighted variables. So let's just think about this just for a brief second. If you think of this as the number of variables here is equal to P, you have P variables. Well, if I have, in the example we started off with, 1,000 different variables, what am I going to have over here? If I have 1,000 variables, this chain of variables is going to become really, really long, right? This chain of variables is going to become really, really long. However, I'm still going to have one Z value here, right? So as I sum up a whole bunch of variables, I'm still generating one particular sum. So when you think of a linear combination, think of it as the sum of all of those observations, right? All of those weighted observations. It's the sum of all those weighted observations. If you think of the linear combination as the right side here, then everything's going to seem really, really weird when you think of principal components analysis, because you're going to think, what am I doing with this big chain of variables, right? I got to carry this big chain of variables around? No, you're carrying around this particular score. And this is being reflected by that particular chain. Otherwise, it could seem strange to calculate variances of linear combinations or other features of linear combinations if you're thinking, how do I calculate the variance of this? Well, this is being reduced into a single score. This is being reduced into a single score. So that's the idea. Okay, that's the idea. So always think of it as a single score. It's being reduced to a single score. Now you can see that, if we really wanted to, if we push the limits a little bit, what if I decided, you know what, I don't want any other variables here. I just want the first variable. Well, the first variable becomes just the single dimension in your analysis. Now you'd never do that because you wouldn't be getting a principal components analysis because you only have a single variable. But when you simplify it, right, that's what you get. Only one variable? Well, there's just one thing to have. The idea of having the linear combination is you want to include other variables into that sum. And again, the idea of the linear combination is not new. We've seen linear combinations in your first stats course in undergraduate statistics. You were studying linear combinations. You just may not have been aware of it, but they are in there. In the t-test is a linear combination. So, you know, when you think of the t-test and you have one mean, right, minus another mean, you're producing a linear combination. Mean 1 minus mean 2 in the numerator of a t-test, you have a linear combination because you're weighting each mean by a particular scalar. So the linear combinations are all over the place. Different from this, it's not the same as this, but it's still a linear combination. So what do we want to do? Well, he said we want to optimize something. So we want to optimize, here's the optimization problem, right? So it reduces down to an optimization problem, right? What are advanced statistics about? It's about optimizing some function, right? It's about optimizing some function. So what do we want to do? Well, I said minimize, maximize. What do we want to do in least squares regression? We want to minimize those sum of squared errors. Want to minimize the sum of squared errors. That's how we're fitting that particular line in least squares, ordinary least squares regression. Well, in the principal components analysis, this is what we want to do. We want to maximize the variance. Okay, we want to maximize the variance of the components subject to the sum of squared loadings is equal to 1. Okay, we want to maximize the variance subject to those squared loadings equal to 1. So there's our weight, there's our variable, and we have our n over here. That's going to go in the denominator, and you're trying to maximize that function, but subject to this. Now, this subject to this is what we just talked about, right? Is subject to the sum of squared loadings equal to 1. I just want to point out this isn't the most interesting part, right? You're not thinking, wow, principal components analysis, the subject of the sum of squared loadings equal to 1 is really interesting. This is kind of like a side note, right? It's a side note. Maximizing the variance, right? Maximizing the variance is the key idea. So, you know, when we think about this, you have the variables in your data set. Well, you want to extract a component, right? You want to extract a component. The first principal component, loading vector, is the one that maximizes the variance. So that first principal component vector is going to have the maximum variance of all the components. And what's it doing? It's maximizing the variance in your variables. Okay, so it's maximizing the variance in your variables. Hence, the objective that we are maximizing is just the sample variance of the n values, right? It's just the sample variance of the n values of our components. So this is the same thing we said. We refer to Z1 all the way to Zn1 as the scores of the first principal component. You're maximizing that. Now, when we say maximizing, you say, well, give me the component that expresses the most variance. That's going to be your first principal component. That's why we're calling it the first principal component. The second principal component is going to be maximized similar to this, but it's also going to have another constraint imposed on it. Okay. So again, just to reiterate this a little bit, this is the exciting part. This is less so. This is so things kind of work out nicely and the weights don't inflate. But this is what you want to do. You want to maximize the variance. So how do you solve this problem? How do you solve this optimization problem? Well, it can be solved. It doesn't have to be, but it can. Good word choice there by the authors, right? It can be solved by eigen decomposition, which is a technique in linear algebra. Details are outside the scope of this book. Well, we've talked about eigen decomposition a little bit. So you have kind of your foot in the door into what's going on with that a little bit, the extraction of eigenvalues and eigenvectors. So that's how we're going to get the components. I've talked about this geometric interpretation. We say that the first principal component, the loading vector, right? You're going to have a loading vector with the elements. Those are the different elements of the loading vector for the different observed variables. That defines a direction in the variable space, the feature space, along which the data vary the most. Now that's exactly what we just said, because we said that the first principal components is going to maximize the variance. That's what this line is actually saying. It's maximizing the variance where they vary the most. Okay. So if we project the n data points, so you have a whole bunch of data points onto this direction, the projected values are the principal component scores themselves. Now there's a lot going on here to make sense of what PC is actually doing. You're taking the original n data points and you're projecting them. So in other words, you're putting them on the principal components, right? You're taking the original values in your data set and you're saying, let's transform this information onto C1, C2 for a 2-component problem. Then these scores on the components, these are projections of the original n scores that you have here. That's what that sentence is actually saying. So the idea of the projection, right? The idea of the projection. You can think of a projection in least squares x, y, as you're taking x and y and you're projecting onto the line. Okay, that's a very convenient way of likening those two concepts. So don't be turned away by this idea of project. All it means is you're taking the n scores and you're putting them on new dimensions, and that's what we're doing when we're projecting. Now, we said this is the first principal component up here. That's the first one. Maximizes the variance. Well, I told you, I said, if you have 10 variables, you're going to have 10 components come out. Unless you have a really, really dysfunctional matrix, you can argue that it's going to be impossible to compute that. But in most cases, if your matrix is well behaved and everything is okay that way, you're going to have those 10 components come out. The first component is going to maximize the variance. The second component, so we're going to choose our second component, right? The algorithm is going to select a second component. It's going to compute the second component. That's also a linear combination. That has as well maximal variance out of all linear combinations. Okay, so it has maximum variance, just like the first component had maximum variance. So this idea of maximum variance is repeating itself. But there's another condition we impose. So we have to impose 3 conditions on that second component. They don't mention the second one here. The sum of squared loadings has to equal 1. This here still has to hold. So that second component is being selected, so it's maximizing the variance subject to this, which again, I said isn't the very exciting part, but we still have to satisfy that constraint. But we also want to satisfy another constraint. Well, what's the other constraint we want to satisfy? We want to satisfy the constraint that it's uncorrelated with Z1. It's uncorrelated with Z1. So in other words, that first component that we extracted, we don't want the second component to be correlated with it. Okay. The second component that's being extracted, we do not want it to be correlated with Z1. So there's our second component scores. Those are all our component scores. That's what takes the form of the linear combination, but it's going to be uncorrelated with Z1. Now, there's also another way of saying this. They're not equivalent ways. One basically implies the other, and this is often kind of like the better way of actually saying this actually. And we know what orthogonality means because we studied matrix algebra at the beginning of the course, but orthogonal means perpendicular. So what they're saying here is they say when it turns out that constraining Z2, the second component, to be uncorrelated with Z1, ends up being the same thing as constraining the direction to be orthogonal to the direction of those weights. So, that's kind of like technical lingo for just saying that they're going to be at right angles. C1, C2, it's a right angle. It's orthogonal, it's perpendicular. Okay, that's perpendicular right there. They also end up being uncorrelated. So this idea of uncorrelated and orthogonal, in this particular case, you can think of them as meaning the same thing, even though they don't mean the same thing. And just be aware that they don't necessarily mean the same thing. Uncorrelated is not an equivalent form of orthogonality. It doesn't mean the same thing. But as they're saying here, it turns out is equivalent to them being orthogonal. But don't say, you don't want to say uncorrelated is the same thing as orthogonal, because it isn't. Perpendicular right here, so that the variance accounted for by C1 is going to be independent of the variance accounted for here. It's not going to be related to it. Okay? And you can think of that, statistically, that's interesting, but substantively, that's interesting too, right? Why is it interesting substantively? Because if your first component is accounting for 70% of the variance, well, you don't want the second component to kind of overlap with that. You don't want Venn diagrams like that. You want C1 to be here and C2 to be here, right? No overlap. And that's a nice feature to have. And the question as to how are they uncorrelated or orthogonal, well, that comes down to the eigenanalysis. So when you do the eigenanalysis, it's pulling out uncorrelated orthogonal, okay, it's orthogonal eigenvectors. So the eigenvectors are going to be orthogonal to one another. Here's an example of a PCA. So we have some variables here. We have murder rate, we have assault, we have urban population, and we have rape over here. And these are different crimes that were measured in a particular city at a particular time. So these are 4 observed variables. We do the principal components analysis on this. We're going to pull out 2 components, okay? Even though, how many components are you going to have? You're going to have 4. You're going to have 4 components because you have 4 observed variables, right? In this case, they're just looking at the first 2. Why? Because probably PC3 and PC4 weren't that interesting. Okay. These are barely interesting. But the 3rd and the 4th are probably going to just throw them out and say, let's just throw these out. So let's focus on the first 2. So when you look at this, you have to ask yourself, well, I've transformed the data, right? I've issued a transformation on the data, and then you want to maybe look at PC1 in more detail. These here are the loadings that we were talking about earlier. Those are the loadings. And when you look at this, you ask the question, you might be interested in asking this question, what is this component made up of, right? What is this component possibly called? You might want to name the component. So if you look at this, component 1 seems to be made up of, if you had to call it something or identify it, we say, well, it's made up of mostly murder, assault, and rape. Urban population doesn't load quite as highly as the other 3 variables. So you may draw the tentative conclusion that PC1 is actually something, a dimension that represents murder, assault, and rape primarily. Now, it doesn't do it perfectly or anything like that. You don't want to say PC1 is is equal to murder, assault, and rape. No, it's just that these load higher than urban pop in this particular data set. Now, if you add other variables, here's the big problem, right? And I know when we go here, it's like, oh my goodness, right? Now it gets complicated because look, you have murder, assault, urban pop, and rape. If you add another variable, X5, X6, X7, and you redo the eigen decomposition, well, all of that stuff is going to change a little bit, right? So when you look at a particular component, you're always looking at the component relative to the variables on which the component analysis was done. Okay, that I can't stress that enough as how important that is. Otherwise, things start to change. Why do things start to change when you add more variables? Just because you're decomposing a different matrix. You're not decomposing a matrix of these 4, you're decomposing a different matrix. So that means that the weights are going to change and the conclusion might possibly change. So remember last week we talked about like the candidate predictors. And that's kind of my word for it, this candidate predictors, because the variables you actually select for your analysis into the candidate predictors, I mean, that's really, when you think about it, like the most important part of everything, given what we know about statistical modeling and how models work and how eigen decomposition is a function of the variables you're operating on. Boy, make sure you get this right. And that's why I said last time, I think I said, spend 10 months getting your model just right, do your research really well, and then interpreting your model. Because if you get that wrong, if you don't have the right candidate predictors, then really your model falls under a lot of criticism, and your analysis falls on a lot of criticism because it's really not specified properly. So assuming that we've got some variables of interest here, we recognize the component solution would change if I had more variables. But for this particular set of variables, I'm thinking that the first component is made up of, or at least dominated to some extent, by murder, assault, and rape. How about PC2? Well, PC2 looks like urban population is the dominant one there. So you can almost say that, although this one's pretty good, that's a little bit the higher one, relatively speaking. So you might want to say that PC2, it's made up of primarily of urban pop. So we have maybe PC1 is having the murder, assault, and rape, and PC2 is the urban pop. Okay. Why don't we take a quick break? We'll come back and we will briefly talk about the biplot up here, which is a visual depiction of the principal components analysis. And right off the bat, you can see on principal component number 1, right here, what we just mentioned, right? Urban pop, it's on its own up here. Rape, assault, and murder looks like they're together over here. So it's exactly what we saw when we looked at the first principal component. So we'll briefly talk about this, and then we'll continue on with PCA. And then hopefully by the end of today, we will just introduce the idea of factor analysis and talk a little bit as to why it's not the same as PCA before we complete that factor analysis idea in full by next week. So take a quick break. We'll be right back.